Among the thousands of exoplanets discovered beyond our solar system, none has yet proven to be more welcoming to humanity than Earth. Some of these distant worlds are consumed by the relentless heat of nearby stars, while others lie locked beneath endless ice or are bombarded by lethal radiation. Yet within this vast collection of hostile environments, there exist planets of a very different kind. On their surfaces, oceans and rivers may flow, clouds drift across alien skies, and rainstorms and lightning shape their atmospheres. It is possible that such worlds could become cradles for extraordinary and unfamiliar forms of life, much as Earth once did. Today, we will explore some of the most remarkable of these candidates. Life is undeniably one of the most astonishing, complex, and enigmatic phenomena in the universe. Despite centuries of study, many fundamental questions remain unanswered. Perhaps the most profound of them all is whether biological life is widespread beyond Earth. At present, we cannot state with confidence whether Earth's biosphere is a rare cosmic exception or the natural outcome of universal evolutionary processes. It is therefore no surprise that the search for extraterrestrial life has become one of the most important pursuits in modern science. To identify the most promising worlds, scientists rely on a metric known as the Earth Similarity Index, or ESI. This index is primarily based on two parameters: surface gravity and equilibrium temperature. Together, these values help determine how closely a planet resembles Earth and how suitable its surface conditions might be for life. One of the ESI's greatest strengths is its simplicity. When an exoplanet is discovered, astronomers can usually estimate its orbit, mass, and size, data sufficient to calculate the index. However, despite its usefulness, the ESI overlooks many factors critical to sustaining life. For this reason, we can attempt a more comprehensive evaluation by expanding upon the ESI with additional parameters. One such factor is the activity of the host star. Frequent stellar flares and powerful ejections of stellar material, common among red dwarfs, can severely destabilize a planet's atmosphere and radiation environment. Even so, red dwarfs are still considered more favorable than massive stars like Sirius or Vega, whose short lifespans and intense radiation leave little opportunity for life to emerge. The most hospitable stars appear to be yellow and orange dwarfs, including our own Sun. Another important consideration is tidal locking, which depends on the distance between a planet and its star. Worlds orbiting too close often become locked, permanently presenting one hemisphere to their star. This results in extreme temperature contrasts between the day and night sides. Conversely, planets located too far away fall outside the habitable zone where liquid water is unlikely to exist. The planet's composition is equally crucial. Life as we understand it requires specific chemical elements and surface conditions typically found on rocky, terrestrial planets, or so-called super-Earths. Mini-Neptunes lack solid surfaces, while ocean worlds may be deficient in essential elements. Taken together, these parameters allow for a more holistic assessment of an exoplanet's potential habitability. Within such a framework, Earth naturally emerges as the ideal benchmark. Mars, while having the highest Earth Similarity Index in our solar system, after Earth itself, is too cold, too small, and lacks sufficient water. Venus, despite its similar size, suffers from an extreme greenhouse effect that makes its surface lethally hot, effectively negating its otherwise favorable characteristics. As a result, no planet within our solar system can truly be considered Earth-like in terms of habitability. Beyond our system, however, more than 5,000 exoplanets have already been discovered. Some of them share striking similarities with Earth. One of the closest is Gliese 1002b, located just 15.2 light-years away. Discovered in 2022 using the radial velocity method, this planet orbits a small, dim red dwarf known as Gliese 1002. The star itself is significantly smaller and cooler than the Sun, with a luminosity roughly 700 times weaker. Gliese 1002 GE lies near the outer edge of its star's habitable zone and completes an orbit every 10 Earth days at a distance of just 0.046 astronomical units. Due to this proximity, the planet is likely tidally locked. It receives about 1.5 times less energy from its star than Earth does from the Sun, giving it an estimated average surface temperature of approximately 230 Kelvin, slightly warmer than Mars. With a possible greenhouse effect and tidal heating, liquid water could exist on its surface, particularly near the boundary between day and night. The planet's mass exceeds Earth's by about 8%, while its radius is only 3% larger, resulting in surface gravity very similar to our own. These factors suggest that Gliese 1002 GI is a rocky world, largely covered in ice, with an Earth similarity index of 0.86. Climate models indicate that its illuminated hemisphere could host oceans with island chains or even continents, while tidal heating may sustain subsurface oceans beneath the ice on the dark side. Gliese 1002b is not alone. A second planet, Gliese 1002c EIE, orbits farther out at 0.074 astronomical units and completes a revolution every 21 days. It receives far less stellar energy, resulting in a surface temperature around 182 Kelvin. Conditions there may resemble those on the icy moons of Jupiter or Saturn. Volcanic activity could potentially support a hidden ocean beneath the surface, creating environments where exotic life forms might arise. Among warmer and potentially more hospitable worlds is K272e, located 217 light-years away. This planet orbits a small red dwarf and lies within its habitable zone. Despite the star's low luminosity, K272e receives slightly more energy than Earth and could maintain an average surface temperature around 295 Kelvin. However, tidal locking and frequent stellar flares pose significant challenges to atmospheric stability. K272e is about 29% larger than Earth and more than twice as massive, resulting in stronger surface gravity. These characteristics suggest it is a rocky super-Earth with a dense atmosphere and liquid water. Its Earth similarity index is 0.87. While stellar radiation presents risks, a strong magnetic field in deep oceans could provide protection, potentially producing spectacular auroras far more intense than those on Earth. Life on such a planet would likely differ greatly from Earth's. Plants might use alternative pigments for photosynthesis, giving them purple or reddish hues. Organisms could evolve thick skin or radiation-resistant cells, similar to extremophiles found on Earth. The system also contains several other planets, some of which are likely barren and Mercury-like, while others resemble Venus in their extreme conditions. If we venture even farther, about 1,800 light-years away, we encounter Kepler 452b, a super-Earth orbiting a Sun-like star. Discovered in 2015, this planet lies comfortably within the habitable zone and completes an orbit in 385 days. Its mass is about 5 times that of Earth, and its gravity is more than double, allowing it to retain a dense atmosphere and form vast shallow seas. Kepler 452b receives slightly more energy than Earth and may have an average temperature around 300 Kelvin. While this could create conditions similar to Earth's Mesozoic era, an unfavorable atmospheric composition might trigger a runaway greenhouse effect, as may have happened on Venus long ago. Still, the planet is believed to be rich in minerals and geologically active, with smoother terrain shaped by high gravity. Life on Kepler 452b could be abundant, especially in its warm, shallow seas. On land, sturdy plants and compact animals with strong skeletal structures might dominate. High gravity could hinder flight, though a dense atmosphere might compensate. Whether such a world truly supports life remains uncertain, and years of research lie ahead. Each year, hundreds of new exoplanets are discovered. Some are hostile and dangerous, others intriguingly Earth-like. Yet despite all our observations, Earth remains the only world we can call home. Every step of human progress leaves its mark upon it, and we cannot say when those marks may become irreversible. For now, preserving our planet is not just a choice, it is a necessity. And let us stay connected.